Hey everyone, my name is Stanley, and today we're going to be going over proving and doing some example solves for the Rolle's theorem and the mean value theorem. So let's go over the Rolle's theorem first. So before we do the Rolle's theorem, you have to meet these conditions. So you have to have this function that is continuous over this closed interval of a to b. Now a to b can be these arbitrary points, you just have this interval of a to b, any two numbers, but that function must be continuous over that interval. And the other thing that you also have to make sure for that function is that that function has to be differentiable over that open interval of a to b. And any single point there must have some derivative there. But what are some things that don't have a derivative? Well, for example, let's say you had this graph and you had this absolute value function. Now you assume that this is a, assume that this is b. What is the derivative of this point over here? Well, this point over here is called a cusp. And what cusp is it's really just the turning point for an absolute value function. But what's the derivative of that? Well, is it the derivative based on this line or this line? We don't know. And it's not zero either. The cusp of an absolute value function does not have a derivative, meaning that point right here is not differentiable. Now, because it's not differentiable, that means the Rolle's theorem does not apply in this case. Okay, so if we have a function in that interval that is both continuous and differentiable, now we can proceed. So assume that f of a equals to 0 and f of b equals to 0. Now, what does that mean? That means that a and b are going to be the x-intercepts. So essentially the function, the interval of a and b can be just any numbers, but the numbers have to be where the function meets the x-axis. So that's why f of a would equal to 0, and that's why f of b would equal to 0. It's because they have to be x-intercepts of that function. So if we know that a and b are x-intercepts, then there exists at least one point, we're going to call that c, where in that interval of a to b, that point c, the derivative at that point is equal to 0. So let's look at a graph. Let's look at this example here. So we see that this function crosses the x-axis at a and at b. So we're going to consider the interval a to b. Now, the function between a to b, it's kind of this semicircular sort of shape, this curved shape. But at this point over here, at point c, as you can see, the derivative of that point is actually 0. Because it's like a turning point of this function, this curved function. Now the turning points of this curved function, it would be 0. So in this case, Rolle's theorem works. And we know that, we have to check, we know that between a and b, this is completely continuous and it's completely differentiable. Every single point has a derivative between the interval a and b. But the c value, even though in this graph there was only one c value, it's not just limited to one. There could be many c values. In fact, there could be, infinite c values. If you assume that there is this graph, right, and then you have this function, let's change the color. Let's say you have this function that just is on the x-axis. Well, we know that there are two values in which a and b are, f of a and f of b are 0. But everywhere in between, every single point in between, the c value is, well, there's infinite c values because all the values in between have a derivative of 0. Yeah, but in this case, we have another curved function. We can see that there's this x-intercepts of a and b. So we can take this interval between a and b. Now, how many c values are there in here? Well, in this function, we can see there's a turning point here, meaning the derivative is 0 at this point. And there's another turning point here, meaning the derivative over there is 0 as well. So in this case, there are two c values. Okay, so let's do an example. Find the c values guaranteed by Rolle's theorem for the following function. Now we're given f of x is equal to x squared minus 5x plus 4. We know that, actually we don't know what the interval is. We don't know what a to b is. It could be anything in this case. We don't know. And we also don't know what the c value is, but we're trying to find it. So let's try finding the interval first. We know the interval has to be x-intercepts of the function. So let's factor out this function. X squared minus 5 plus 4 can be factored into x minus 4 times x minus 1. So in this case, we get values of x as 4 and 1. And in this case, 4 and 1, those points are going to be the x-intercepts of f of x in this case. So now, we know what the interval is. We know it's 1 to 4. So now we have to find the c value. Well, we have to first meet Rolle's theorem's conditions before we actually do the math to find c. So since f of x is continuous, we know that it's continuous and differentiable over that interval. But how do we know that? Well, f of x, we're given, it's a polynomial. It's x squared minus 5x plus 4, it's a polynomial. And all polynomials are continuous and differentiable over the domain like negative infinity to infinity. It will always be continuous and differentiable no matter what point it is. So, because it's a polynomial, it will fit the conditions of Rolle's theorem. And therefore the hypothesis of Rolle's theorem is met. So now we can actually solve for c. So how do we do that? Well, we know that the derivative of c is going to be equal to 0. So let's take the derivative of the function. F prime of x is equal, let's use the power rule in this case, and we get 2x minus 5. So now that we have the derivative, we can plug in c into the function. So we get the f prime of c, or the derivative of c, is equal to 2c minus 5. And we know that because there is this c value in which the derivative of that point is 0, we can just substitute 0 for f of prime of c. And now we're left with 0 equals to 2c minus 5. So in this case, we just solve for c, and we get c is equal to 5 over 2. So that is the c value that we found, but we have to make sure that c value is in the interval, as it might not be. So, is 5 over 2 between 1 and 4? Yes, because 5 over 2 is 2.5, and that is between 1 and 4, and therefore the c value in this case is 5 over 2. All right, so let's look at a graphical example of this problem. So given this graph, we graph the function in this case. As you can see, there's x-intercepts of 1 and 4. So we're trying to find a c value in this interval in which the derivative of that c value is 0. And we know it's 0 at this turning point for the function. And what is that turning point? It's 5 over 2. Here's a number line of the derivative. As you can see, so for this number line, the derivative is 0 at 5 over 2, negative before it and positive after. That's basically just modeling this graph over here. Okay, so let's continue and move on to the mean value theorem. So like the Rolle's theorem, the mean value theorem also has these conditions where you have to meet before you actually solve for that c value. Now in this case, it's still the same, the conditions. We're letting the function to be continuous and differentiable over some interval of a to b. Except this time, a and b do not have to be x-intercepts. They do not, like f of a and f of b do not have to equal 0. So what the mean value theorem says is that there is at least one point c in a and b, which are supposed to be points of a function, x values of some function. There's at least this one point c where we get this equation here. F prime of c is equal to f of b minus f of a over b minus a. What does that mean? Well, we know f prime of c is the derivative of c. So at least there's one point c in that interval where the derivative of c is equal to, and what is this? This is the slope of the secant line between a and b. So essentially you have this interval a and b. You find the secant line, and there is at least one c value there in which the slope of that point at c is equal to the slope of the secant line. So what do I mean by that? Let's look at this graph here. So we have interval a to b. The points of a and b are right here. And we found the secant line right here. Now this slope of the secant line, that is going to be equal to a point c within this interval. The slope of point c within interval a and b. So in this case, it could be right here because the slope is the same as this. So the c value would be here, and that's one c value here. It could be over here as well because the slope is the same as the slope of the secant line between a and b. So there's another c value here. So in this case, there's two c values. Okay, so let's look at how we prove it. So we're given this function in green of f of x, and it's kind of curved, and we have a and b here. So we have the interval a and b. So f of a is going to be right here, f of b is going to be right here, and we're going to make a secant line between that. And we're going to assume that v of x is the difference between the height of the function and the secant line. So it's basically the difference between this function and the secant line. Oops. So as you can see, the v of x is going to increase as it's moving along, and then it's going to decrease after it passes that maximum point. Okay, and it's also important to note that at this point A, v of x is 0 because the difference between it is 0. They're literally on the same point. And so is the same thing for b. Okay, now we can get on to the proof. So we know f of x is the difference between the height of the function and the secant line. So let's put that into mathematical terms. The height of the function minus the secant line is essentially what it is. So what is the function? It's f of x. Minus what is the secant line? Well, let's ignore this part for now. So how do we even find that? Well, the secant line, let's use point slope form. If you remember what that is, that's y minus y1 equals m times x minus x1, where x1 and y1 is some point on the function. Okay, so we know f of a is a y value that's on the function, and a is a value that's on the function, because the coordinates of a, f of a, are on the function, as you can see over here. That's the point, a, f of a. So we plug this into this equation. We get y minus f of a is equal to some slope times x minus a. Now what's the slope? The slope of the secant line, as we said before, is kind of just rise over run. It's this difference minus this difference. So essentially it's f over f of b, which is at this height, minus f of a, over b, which is over here, down here, minus a. So that's the slope here. So we plug that in here. And now we can change it so that we can bring the f of a to the other side so that we isolate y. Now we can plug this entire equation for the secant line back into the original equation for v of x. But what do we do now? Now that we have this equation, let's just take the derivative of v of x. But why do I do that? Well, we know, and it's kind of evident from the graph, that at the highest point of v of x, that's where the slope of that point is equal to the slope of the secant line. Okay, so let's take the derivative of v of x in this case. So we get f prime of x minus Now this looks kind of hard, but know that f of a is a constant, and a is a constant as well. We know that from the graph over here, that these are just both constants. So we can kind of ignore a in this case, meaning the derivative of negative, this slope times x is just minus this. So we just have this right here. And then because this is a constant as well, any derivative of a constant is going to be 0. So we can just ignore that completely. So now we have v prime of x equals to f prime of x minus f of b minus f of a over b minus a. Now, as we said before, the maximum value of v of x is where that point is going to, the slope of that point is going to be equal to that slope of that secant line. So let's set v prime of x to 0. And then now let's bring, because this is minus, we can bring this to the other side. And essentially we get the equation f prime of x equals to f of b minus f of a over b minus a, where that point of x is c. And so now we've gotten the same equation as we had before, right here, where some point of c between this interval of a and b is going to be, the slope of that point of c is going to be equal to that secant line between the interval of a and b. So right here, this is our equation. So let's do a practice problem. So we're given this function f of x equal to 1/4 times x cubed plus 1. And we want to find the c value guaranteed by the mean value theorem over some interval, and we're given the interval in this case, which is 0 to 2. So let's use this equation that we had originally. What's the f prime of c? Well, if we plugged in c into the equation, we would have f of c is equal to 1/4 c cubed plus 1. So what's the derivative of that? Well, we can use the power rule and get 3/4 c squared plus 0, because the derivative of 1 is 0. So that's why we just have 3/4 c squared in this case. Now, we do want to set this equal to f of b minus f of a over b minus a. Now, what's a and b in this case? A is 0, b is 2. So, essentially, we're finding f of 2 minus f of 0 over 2 minus 0, which is just 2. So, what is f of 2? What is f of 0? Well, we have to plug into the original equation here. So, f of 2 is just equal to 2 cubed, which is 8, divided by 4, which is 2, plus 1, which is 3. So, f of 2 is 3. What's f of 0? Well, 0 cubed is 0, 0 times 1/4 is 0, plus 1 is 1. So f of 0 is 1. So essentially we have 3/4 c squared equals to 3 minus 1 over 2. Now, therefore, it's 3/4 c squared equals 2 over 2, which is just 1. Now we multiply 4/3 on the other side, and we get c squared equals to 4 over 3. So now, in order to find c, all we have to do is square root both sides, and we get c is equal to plus or minus 2 over rad 3. And it's because the square root, it can be plus or minus for the answer. But, however, even though you got two answers for c, you have to make sure the c value is between a and b. So we have these two answers here. And we have to make sure they're between a and b. But if you take a close look at this, this is a negative number. And yet a and b is from 0 to 2. Oh, sorry. It's from 0 to 2. So, therefore, this cannot work. This is not a c value between that interval. What about this one? Well, 2 over rad 3. We know rad 3 is around like 1.7. So 2 divided by 1.7 is around 1 point something. And that is within 0 and 2. So we know that this must be the c value within that interval in which the slope of this c value is equal to the slope of that secant line between 0 and 2. And so therefore c is equal to 2 over rad 3. We're not going to rationalize here just for the sake of time. Okay, so that's essentially what I had for the Rolle's theorem and the mean value theorem. You know, if you're interested in any similar content like this, be sure to check out our channel at Task Team. There's going to be some homework with some similar questions for the Rolle's theorem and the mean value theorem, which is linked in the descriptions below, and so are the answers. It's also linked in the description below for you to try out those questions if you would like. So I hope everyone has a nice day, and I'll see you in the next video. Bye.